You think you know what keeps you alive? Oxygen, water, maybe sunlight? But there's something else, an invisible force wrapping around this planet like a shield. 3,000 kilometers beneath your feet, a metal ocean churns at speeds reaching tens of kilometers per year. That motion creates Earth's magnetic field. Without it, solar wind would strip our atmosphere to nothing. Mars learned that lesson billions of years ago. But here's what nobody tells you. The shield flips, north becomes south, south becomes north. The last time it happened was 780,000 years ago. We're overdue. And the mechanism behind these reversals is stranger than you ever imagined. Something that scientists at institutions from Kyoto University to the German Research Center for Geosciences are only now beginning to decode. The measurements coming back from satellites orbiting Earth right now show patterns that shouldn't exist. Magnetic field lines retreating back into the core instead of extending outward. A weak spot over the South Atlantic growing by 5 million square kilometers. Electric charges on the morning side of the magnetosphere reversed from everything we predicted. In October 2025, researchers published findings in the Journal of Geophysical Research showing the morning side carries negative charge. Not positive. Yusuke Ebahara and his team at Kyoto ran simulations that matched satellite data perfectly. The field we thought we understood for decades was backwards in key regions. If you value documented geophysical history and cutting-edge magnetic field research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Journal of Geophysical Research Space Physics, published October 31st, 2025, findings from the European Space Agency's swarm mission data, analyzed through 2025, and the Mathematics Journal's February 3rd, 2024 publication on magnetic reversal predictability by Danil Tolmachev's research group. These aren't generic sources. These are the deep measurements showing us what's actually happening inside our planet. Now back to the information. Temperature matches the surface of the Sun, 6,000 Kelvin at the inner core boundary, 3,800 Kelvin where the core meets the rocky mantle above. That temperature difference drives everything. Hot metal rises, cool metal sinks. But Earth rotates. The Coriolis effect twists those convection currents into spiraling columns aligned roughly north to south. Moving metal conducts electricity. Moving electricity generates magnetic fields. That's the geodynamo. A natural generator that's been running for at least 3.5 billion years. A refrigerator magnet hits 50,000 microteslas, but it's enough. The magnetosphere deflects charged particles streaming from the sun at speeds up to 800 kilometers per second. Without that deflection, those particles would ionize our atmosphere, strip away the ozone, bombard the surface with radiation that would make complex life impossible. We know this because we can see the corpse of a planet that lost its field, Mars. Its core cooled. The dynamo stopped. Solar wind tore away most of its atmosphere. Surface pressure dropped to less than 1% of Earth's. Any water evaporated or froze into the soil. The North Magnetic Pole has been tracked since 1831 when Sir James Clark Ross found it in northern Canada. For most of recorded history, it drifted slowly. Then something changed. In the past 20 years, it accelerated toward Siberia. 55 kilometers per year in 2007, according to the Canadian-French survey. Then, 5 years ago, it decelerated from 50 to 35 kilometers per year. That's the biggest deceleration ever measured, according to Dr. William Brown at the British Geological Survey, speaking in January 2025. Nobody knows why. Measurements over the last 200 years show a 9% global decline. But the weakening isn't uniform. Over the South Atlantic, between South America and southwestern Africa, there's a massive dent in the field, the South Atlantic anomaly. ES's 3 swarm satellites have been mapping it since 2014. The data published in Physics of the Earth and Planetary Interiors in November 2025 shows the anomaly has expanded by an area nearly half the size of continental Europe. That's roughly 2 million square miles in 11 years. And since 2020, the rate of weakening has accelerated. His group compiled 11 years of satellite measurements. The results are clear. The anomaly isn't a single block. It's changing differently toward Africa than near South America. Beneath the South Atlantic anomaly, magnetic field lines that should be extending outward from the core are bending back into it. These reverse flux patches sit at the core mantle boundary. Finley's team detected one drifting westward under Africa. That motion is driving the faster weakening on the African side. So do thousands of low Earth orbit satellites. When they enter the anomaly, energetic protons strike their electronics. Circuit boards short, data corrupts, systems crash. The Globalstar satellite network failed in 2007. Multiple failures clustered over the anomaly. Hubble Space Telescope shuts down its UV detectors when passing through. The radiation would damage the sensors. Astronauts report seeing shooting stars in their vision, phosphenes. Cosmic rays striking their retinas directly. Skylab's Apollo telescope mount triggered false solar flare alarms every time it crossed the anomaly. The Pamela experiment detected antiproton levels orders of magnitude higher than expected while passing through this region for at least 8 million years, possibly up to 11 million. The cause sits 2,900 kilometers down at the core mantle boundary. Beneath southern Africa, there's a massive structure called the African Large Low Shear Velocity Province. It's a huge reservoir of unusually dense rock. Seismic waves slow down dramatically when passing through it. The structure is roughly the size of the continent above it. Geophysicist Weijia Kwang at NASA Goddard explained in 2020 that this dense rock disrupts heat flow from the core. Cooler regions in the mantle above the African structure pull more heat from the core below. That altered heat flow changes convection patterns in the liquid outer core. Changed convection means changed magnetic field generation. The South Atlantic anomaly might be more than a local oddity. Some researchers think it's a warning sign, a precursor to something much bigger, a full magnetic reversal. The transition from normal field to reversed field lasted about 250 years. The field stayed reversed for roughly 440 years. Then it flipped back. This wasn't a full reversal, it was an excursion. The Lachaume event, named after lava flows near Clermont-Ferrand, France, where geophysicists first detected the anomalies in the 1960s. During the transition, the field weakened to 5% of its current strength. When fully reversed, it sat at about 25% of normal. The dipole structure collapsed. Instead of two poles, multiple poles appeared across the planet's surface. These are high-energy particles, mostly protons and atomic nuclei, traveling at relativistic speeds. Normally, Earth's field deflects them, but at 5% strength, they punched through. When cosmic rays strike atmospheric atoms, they create cascades of secondary particles. One of those particles is beryllium-10. It's radioactive with a half-life of 1.36 million years. It accumulates in ice and ocean sediment. Scientists can drill cores and measure beryllium-10 concentrations. Higher concentrations mean more cosmic rays hitting the atmosphere, which means weaker magnetic field. Sanja Panofska at GFZ Potsdam, Germany, reconstructed the magnetic field during the Lachaume event, using both paleomagnetic data and beryllium-10 measurements from ice cores and marine sediment. Her findings presented at the European Geosciences Union General Assembly in April 2024 show beryllium-10 production doubled during the Lachaume excursion, double the cosmic rays. The magnetosphere shrank when the field decreased. Less shielding, more radiation reaching Earth's surface. The study was published in multiple journals through 2024 and 2025. The timing correlates with the extinction of Australian megafauna. Large animals died out. Cave art appeared in Europe around the same time. Some researchers speculate ozone depletion from ionizing radiation, atmospheric circulation changes. Climate shifts, but the correlation isn't proof. Life survived. Humans survived. Neanderthals were already declining before the event. The Lachaume excursion might have accelerated their extinction, or it might be coincidence. The evidence remains contested. The magnetic field briefly flipped 41,000 years ago. The planet survived. Life survived. But we've never experienced a reversal or excursion with modern technology. Satellites, GPS, power grids, communication networks. All of it depends on a stable magnetic field. Evidence. Brunias discovered it in 1906. He measured reverse magnetization in basaltic lava flows at Pont-Forain in the Cantal region of France. The magnetic minerals in the rock pointed south instead of north. Matuyama confirmed it in 1929 with measurements from volcanic rocks across Japan and Korea. A 2004 paper by Bradford Clement estimated several thousand years depending on location. A 2010 paper suggested it could happen within a human lifetime. Then, in 2019, geologist Brad Singer at the University of Wisconsin-Madison published new findings in Science Advances. His team analyzed lava flows from Chile, Tahiti, Hawaii, the Caribbean, and the Canary Islands. They combined magnetic readings with radioisotope dating. The reversal began around 799,000 years ago, when non-dipole field components increased and the axial dipole decreased. The minimum dipole strength hit around 780,000 years ago when the field changed polarity. It stabilized in normal polarity around 770,000 years ago. Total duration? 29,000 years. But the active flip, when the field was actually reversing, took only about 4,000 years. The preceding 18,000 years showed instability, temporary partial reversals, the field trying to flip but not quite making it. Why does it take so long? The solid inner core. It's roughly the size of the moon. 75 9 miles thick, according to NASA measurements, composed mostly of iron and nickel, temperature around 6,000 Kelvin. As hot as the sun's surface, but kept solid by immense pressure. The inner core can't generate magnetic field through fluid motion because it's solid, but magnetic field generated in the liquid outer core can diffuse into the inner core. That diffusion is slow, much slower than the convection in the outer core. They modeled convection and magnetic field generation in the fluid outer core surrounding the solid inner core. The simulation ran for more than 300,000 years of simulated time on supercomputers at Pittsburgh Supercomputing Center and Los Alamos National Laboratory. About 36,000 years into the simulation, the magnetic field reversed. The reversal took a few thousand simulated years. The dipole intensity decreased by a factor of 10, then recovered immediately after. Their model showed that convection in the outer core continually tries to reverse the field, but the solid inner core resists. The field locked in the inner core takes much longer to change. It can only change through diffusion, not convection. Only about 1 in 10 reversal attempts succeeds. That's why reversals are long and randomly distributed. That averages to 1 reversal every 450,000 years, but there's no pattern. The time between reversals ranges from less than 100,000 years to as much as 50 million years. During the Cretaceous period, there was a span of more than 30 million years with no reversals at all. The current normal polarity epoch, the Brunhes epoch, has lasted 780,000 years. That's almost double the average. Are we overdue? Scientists argue about this. Some point to the weakening field and growing South Atlantic anomaly as warning signs. Others say the field has weakened many times without reversing. Finley told reporters in October 2025 that paleomagnetic records show weak field regions like the South Atlantic anomaly appearing throughout history without triggering full reversals. The current changes might be decade to century scale fluctuations, not reversal precursors, but nobody knows for certain. That's the answer from researchers at École Normale Supérieure and Institut de Physique du Globe de Paris. They published their findings in Physical Review E in April 2009. The Earth's magnetic field is primarily dipolar, 2 poles. But the outer core can also generate quadrupolar fields, 4 poles, or even more complex structures. Most of the time, the dipole dominates because it's more easily generated by the convection flow. But under certain conditions, the quadrupole can strengthen. The solar magnetic field reverses every 11 years. North and south swap. The full cycle takes 22 years. For Earth, the coupling is weaker. Oscillations don't happen spontaneously. Small fluctuations in convection velocity can push the system away from the dipole state toward the intermediate quadrupole state. From there, it can be attracted to the opposite dipole polarity. A reversal happens in 2 phases. A slow phase where fluctuations drive the evolution, and a fast phase where the dynamics become self-sustaining and the field flips rapidly. A study published in Scientific Reports in April 2024 by scientists studying numerical dynamo models found that reversals are triggered regionally, not uniformly across the planet. In their simulations, reversals started beneath the Americas and East Asia, where core mantle boundary heat flux is anomalously large. More heat extracted from the core in those regions. Stronger convection, greater inertial effects. The turbulence fragments magnetic field structures. Eventually, that regional fragmentation cascades into a global reversal. The outer core flows at tens of kilometers per year, different timescales, but they're coupled through heat transfer. Plate tectonics and mantle convection change how heat flows from the core into the mantle. Cooler mantle pulls more heat from the hot core. That changes convection patterns in the outer core. Changed convection means changed magnetic field. A study led by A. Biggin at the University of Liverpool and published in Nature Geoscience in July. 2012 showed connections between reversal frequency and mantle processes. When mantle convection accelerates heat extraction, the outer core responds. The magnetic field becomes less stable. The African Large Low Shear Velocity Province might be key. It's been sitting beneath southern Africa for millions of years. It affects heat flow at the core mantle boundary. Research shows it correlates with both the South Atlantic anomaly and with changes in reversal frequency over geological time. But the exact mechanisms remain unknown. Haggai Amit at Nantes Université in France, who studies the South Atlantic anomaly, noted in October 2025 that several mechanisms have been proposed but none proven. Daniil Tolmachev and his team introduced a new approach in February 2024. Published in Mathematics, their study used mathematical modeling to identify early warning signals of geomagnetic reversals. They discovered patterns in magnetic and hydrodynamic harmonics that could serve as precursors to polarity switches. The Earth's magnetic field has existed for at least 4.2 billion years. Reversals occur typically once every few 100,000 to a million years. Tolmachev's models might offer predictive insight into when the next reversal happens. The study represents a significant leap in understanding Earth's magnetic dynamics. By identifying precursors, they provide tools for potential crisis management. During a reversal, the field weakens by up to 90% according to USGS paleomagnetic records. The dipole structure collapses, multiple poles appear, the magnetosphere shrinks, cosmic ray flux at Earth's surface increases dramatically. Satellite infrastructure would face unprecedented radiation exposure. GPS would degrade or fail. Power grids could see transformer damage from geomagnetically induced currents. Radio communication would suffer interference. High-altitude flights would face increased radiation risk for crew and passengers. The ozone layer would thin from ionization. Skin cancer rates might rise. Agriculture could face challenges from increased UV exposure. If the reversal takes 20,000 years like the Bruni's Matuyama, civilization would have time to adapt, build hardened satellites, redesign power grids, develop new navigation systems. But if it happens in a few thousand years or less, adaptation becomes harder. And during the peak of the transition, when the field is at its weakest, technology will be most vulnerable. Right now, in November 2025, satellites are watching. ESA's 3 swarm satellites, Alpha Bravo and Charlie, launched November 22, 2013. They've been measuring magnetic signals from Earth's core, mantle, crust, oceans, ionosphere, and magnetosphere continuously for over 11 years. That's the longest continuous record of magnetic field measurements from space. The data feeds into models like the World Magnetic Model 2025, released December 21, 2024. The model's resolution improved from 3,300 kilometers to 300 kilometers at the equator. High-definition view of magnetic field variations, critical for tracking the South Atlantic anomaly and other anomalies worldwide. There are 2 strong magnetic field regions in the Northern Hemisphere, one near Canada, one over Siberia. The Canadian anomaly has shrunk by an area the size of India over the last 11 years. The Siberian anomaly has grown by an area the size of Greenland. In the Southern Hemisphere, there's another strong region south of Australia. These variations reflect complex dynamics in the outer core. Chris Finley explains that Earth's magnetic field isn't a simple dipole like a bar magnet. It's the sum of many smaller scale magnetic structures generated by convection throughout the outer core. Each structure evolves independently. The overall field we measure at the surface is the combination of all those variations. They move, they grow, they shrink, they merge. The South Atlantic anomaly sits above a particularly large and active reverse flux patch. As that patch drifts westward under Africa, it intensifies the local field weakening. NASA's Visualization Studio has created animations showing the South Atlantic anomaly from 2015 through 2025, both at Earth's surface and at the core mantle boundary. The correlation is clear. Surface weakness tracks core-level structures. A zigzag in the magnetic field at the edge of our magnetosphere. Similar structures were discovered near the Sun by Parker Solar Probe, but seeing one near Earth was unexpected. The event occurred at the magnetopause, where solar wind pressure balances Earth's field. E.O. McDougall at the University of New Hampshire led the research published in the Journal of Geophysical Research. The switchback featured a twisting patch of plasma that rotated and rebounded. High-energy electrons moved along the field lines, material from within Earth's field. The structure sat in the magnetosheath, the turbulent layer outside the magnetosphere where solar wind flows around our magnetic bubble. MMS measured an active reconnection site, magnetic field lines breaking and rejoining, releasing energy. The Z parameter exceeded 0.5, confirming switchback classification. The deeper question is whether these processes connect to core dynamics. Do surface-level magnetic anomalies reflect churning 3,000 kilometers down, or are they independent phenomena? The answer isn't clear yet. What is clear is that Earth's magnetic field is changing faster than expected. A July 2020 study reported by scientists analyzing simulations and observational models found maximum rates of directional change, reaching 10 degrees per year. That's almost 100 times faster than current changes, 10 times faster than previously thought possible. The field can shift dramatically over human timescales, not just geological ones. ETH Zurich researchers published findings in Nature in July 2025, showing that Earth's magnetic field was generated even when the core was fully liquid, before the inner core crystallized around 1 billion years ago. The dynamo still worked. Yufeng Lin led the study. His team demonstrated the correct physical regime where core viscosity has negligible influence on the dynamo effect. This finding helps interpret paleomagnetic data from billions of years ago. It also shows the magnetic shield protected early life from radiation. Without that protection, complex life might never have evolved. It wanders. It flips. The mechanisms driving those changes emerge from chaos 3,000 kilometers beneath our feet. Liquid iron spiraling in columns, heat flowing unevenly at the core mantle boundary, reverse flux patches drifting westward. The solid inner core resisting change, small fluctuations triggering cascades, a system so complex that the world's most powerful supercomputers struggle to simulate it accurately. The South Atlantic anomaly grows, the magnetic North Pole races toward Siberia, then slows. Field lines retreat into the core, electric charges flip in the magnetosphere, satellites glitch, instruments fail, astronauts see phantom lights. Every measurement adds to the picture, every model gets refined. We're closer than ever to understanding what makes the field flip, but we're not there yet. In 1995, two groups independently created the first self-consistent dynamo models, one in Japan, one in the United States, led by Glatzmeyer and Roberts. The US model gained attention because it successfully simulated geomagnetic reversals. For the first time, scientists could watch a reversal unfold in a computer, see how the field collapsed, how multiple poles formed, how the dipole eventually stabilized in opposite polarity. The simulation proved the geodynamo theory. Convection in the outer core really does generate Earth's magnetic field, and that process can naturally produce reversals. But simulations aren't reality, they use simplified physics, parameters that don't exactly match Earth's core. The Ekman number in Earth's outer core is around 10 to the negative 15. That's extremely small. It represents how rapidly Earth rotates relative to viscosity. Current supercomputers can't simulate dynamos at such low Ekman numbers for long enough to capture reversal statistics. Researchers use higher Ekman numbers, slower rotation. That makes reversals more frequent in models than in reality. Every simulation is a compromise between physical accuracy and computational feasibility. The gap between simulation and reality shrinks. Researchers now incorporate heterogeneous boundary conditions, variable heat flux at the core mantle boundary that reflects real mantle structure, the African large, low shear velocity province, the Pacific ring of fire. All these features affect core convection. Models that include them produce more realistic magnetic fields, better match paleomagnetic data, show regional triggering of reversals, like the research published in scientific reports found. The South Atlantic anomaly is growing. The North Pole is wandering erratically. These could be precursors, or they could be normal fluctuations. The field has weakened many times without reversing. It wandered many times without flipping. We won't know until it happens, or doesn't. Small changes in the outer core's flow can trigger large changes at the surface. The field we depend on for navigation, for satellite operation, for protection from solar radiation, exists at the mercy of convection patterns 3,000 kilometers down. Formed multiple poles, reversed partially, reversed again. The process was messy. Directional changes at the surface varied wildly depending on location. Some sites recorded rapid changes, others showed gradual drift. The geomagnetic latitude mattered. Local non-dipole components mattered. The transition looked different everywhere. Some regions will see rapid field changes, while others remain relatively stable. The South Atlantic anomaly might expand further, or it might stabilize, or it might split into multiple anomalies. The north and south magnetic poles might wander away from the geographic poles, or they might stay close. Multiple poles might appear temporarily, or the dipole might hold. Research from November 2024 on predicting future behavior shows that continuous high-quality measurements are crucial. Without satellites like SWARM, without ground-based magnetometers tracking changes, without paleomagnetic studies of past reversals, we're blind. The data flowing in now will inform models for decades. Every measurement of the South Atlantic anomaly's growth, every tracking of the magnetic pole's motion, every beryllium-10 measurement from ice cores. It all contributes to understanding. Deep rumbling interrupted by high-pitched whines. The Brunhes-Matuyama reversal sounds similar but longer, more drawn out. Technical University of Denmark and the German Research Center for Geosciences created the audio in 2024. 32 speakers, each playing sounds representing magnetic field changes at 32 locations around the world. It's unsettling, an audible reminder that Earth's protective shield is not constant. It fluctuates. It roars and screams in ways we can't normally perceive. We can't adjust heat flow at the core mantle boundary. The forces involved are too large, the depths too great. We're passengers on this planet. The geodynamo does what it does. Underground data centers, lead shielding on spacecraft, improved power grid protection against geomagnetically induced currents, better forecasting for high radiation periods. These are all achievable with current or near future technology. The challenge is cost. Building a fully hardened global infrastructure would be expensive. Most governments and companies won't invest without clear evidence that a reversal is imminent, and we don't have that evidence. We model. We prepare as best we can. The magnetic field will do what it's going to do. It's been flipping for billions of years. It will keep flipping. Maybe next year, maybe in 100,000 years. The planet survived every previous reversal. Life adapted, evolved, thrived. We'll adapt too if it happens in our lifetime, but the transition will be uncomfortable. Technology will break, systems will fail. We'll have to rebuild infrastructure that we currently take for granted. In the meantime, the South Atlantic anomaly keeps growing. Satellites keep glitching when they pass through. The North Magnetic Pole keeps drifting. Heat keeps flowing unevenly from the core into the mantle. Iron keeps spiraling in the outer core. Electric currents keep generating magnetic fields. The geodynamo keeps running. And somewhere in that churning metal ocean 3,000 kilometers down, small fluctuations are happening right now, convection patterns shifting. Reverse flux patches forming and dissolving, the dipole and quadrupole modes interacting, the system balanced on a knife edge between stability and chaos. The coupling between modes will strengthen, the dipole will start to decay, multiple poles will appear, the field will collapse to 10% of its current strength, cosmic rays will flood the upper atmosphere. Satellites will fail in large numbers, GPS will become unreliable, power grids will face cascading failures, and over the course of thousands of years the poles will swap. North will become south, south will become north. Compasses will point in the opposite direction. Navigation systems will need recalibration. The magnetosphere will eventually stabilize in its new configuration, and life will continue, different but continuous. That's the strange truth about Earth's magnetic field reversals. They're catastrophic in the moment, but in geological time, they're routine. The planet doesn't care. The core keeps convecting. The dynamo keeps running. The field keeps existing, just pointed in the opposite direction. What we think of as normal, this current magnetic configuration, is just one phase in an endless cycle. The field has been normal for 780,000 years. Before that, it was reversed for however long the Matuyama epoch lasted. Before that, it was normal again, on and on back through time. Years. The pattern is clear in magnetic stripes on the seafloor. As new oceanic crust forms at mid-ocean ridges, iron-bearing minerals in the cooling magma align with the magnetic field. That alignment gets locked in as the rock solidifies. The crust slowly spreads away from the ridge. Over millions of years, a magnetic tape recording of field reversals gets laid down. Black stripes where the field pointed north, white stripes where it pointed south. The stripes are symmetric on both sides of the ridge, proof that the field flips affect the entire planet simultaneously. That discovery in 1906 launched the field of paleomagnetism. Now we can read Earth's magnetic history in volcanic rocks, in sediment cores, in archaeological artifacts, pottery kilns, ancient bricks. Anywhere iron-bearing materials cooled in the presence of Earth's magnetic field, each sample is a magnetic snapshot. Collectively, they tell the story of a field that wanders, weakens, strengthens, and flips with no discernible pattern. Researchers at the Helmholtz Center for Geosciences in Potsdam, Germany, used paleomagnetic data from drill cores around the globe to construct a global model of the Matuyama-Brunhes reversal. The model describes the temporal evolution continuously using spherical harmonic functions. It shows how the transitional field looked at the core mantle boundary and at Earth's surface. The dipole decayed. Non-dipole components grew. Reverse polarity appeared first in high-latitude southern hemisphere and equatorial regions. The minimum dipole strength occurred around 780,000 years ago. The field stabilized in normal polarity about 10,000 years later. Ahmed Nasser Mahgoub. Ahmed and Monica Korda at GFZ Potsdam worked on this reconstruction. Their model serves multiple purposes: understanding processes in the outer core during reversals, estimating radiation exposure when the field weakens, testing dynamo theory against real data. Every detail matters: the timing of dipole decay, the rate of recovery, the spatial distribution of reversed flux patches. All of it constrains what the geodynamo can and cannot do. That brings us to the most recent discoveries. November 2025. Multiple publications converging on similar conclusions. The magnetic field is more complex than simple dipole theory suggests. Regional variations matter. Reverse flux patches at the core mantle boundary drive surface anomalies. The South Atlantic anomaly is real. It's growing. It correlates with core-level structures. The African large low shear velocity province affects heat flux and therefore magnetic field generation. This was discovered through satellite measurements analyzed by Yusuke Ebihara, Masafumi Hirahara, and Takashi Tanaka, published in Journal of Geophysical Research Space Physics October 31st, 2025. MHD simulations match the observations. The finding reframes how scientists interpret electrical activity in near space. Plasma convection drives charge distribution, not the other way around. Electric force and charge are results, not causes, of plasma motion. The switchbacks are tied to magnetic reconnection, breaking and rejoining of field lines that releases energy. That process heats the solar atmosphere and powers disturbances near Earth. If switchbacks form regularly at the magnetopause, they inject energy into the magnetosphere. They might seed larger storms. They reveal coupling between solar wind and Earth's magnetic field that wasn't fully appreciated. All these pieces fit together. The outer core generates the field through convection. The solid inner core resists changes and makes reversals rare. Heat flow at the core mantle boundary affects convection patterns. Mantle structures like the African large, low shear velocity province create regional variations in heat flux. Those variations trigger regional magnetic anomalies. The South Atlantic anomaly, strong patches over Siberia and Canada. Reverse flux patches drifting westward. Small fluctuations in convection can trigger transitions between dipole and multipole states. When conditions align, the field flips. The transition takes thousands to tens of thousands of years. During that time, field strength drops to 10% of normal. Cosmic radiation increases, multiple poles wander across the surface. Eventually, the field stabilizes in opposite polarity. The process has happened 183 times in the last 83 million years. The SWARM mission has now provided 11 consecutive years of data, the longest space-based record we have. Future missions will extend that further. NASA plans new magnetosphere missions. ESA is considering swarm follow-on satellites. China and other nations are launching magnetometers. The global network of ground-based observatories continues operating. Every data point refines our understanding. The piece noted that understanding magnetic field generation is important not just for Earth, but for other bodies. Magnetized rocks from the Moon and ancient meteorites show that smaller bodies once had active dynamos. Mercury has a weak but active field despite its small size. Venus has almost no field despite being similar to Earth in size. It rotates very slowly, that might be why. Mars lost its field when its core cooled. Every planet tells part of the story. Earth provides the most complete data, because we can measure its field continuously from inside the magnetosphere. You need a liquid electrically conductive outer core. You need sufficient heat to drive convection. You need rotation to organize the flow. You need time for the system to stabilize. Earth has had all these for billions of years. Mars had them early, then lost them. Venus has the heat, but not the rotation. Mercury has rotation, but a small core. Each planet evolved differently. Their magnetic histories diverge. We have the right combination of factors. Large iron core, vigorous convection driven by heat from radioactive decay and latent heat from inner core crystallization, rapid rotation organizing flow into columns. A thick, rocky mantle providing thermal insulation, an atmosphere protected by the magnetic field, allowing liquid water on the surface, allowing life. All the pieces fit together. Doing what it's always done. What it will keep doing for billions of years until the core cools completely, which won't happen for another few billion years at least. The geodynamo is self-sustaining as long as there's energy to drive convection. That energy comes from multiple sources. Primordial heat from Earth's formation, radioactive decay of uranium, thorium, potassium in the core and mantle, gravitational energy released as heavy elements sink toward the center, latent heat from iron crystallizing onto the inner core. All these sources combine to maintain the temperature difference between inner core and core mantle boundary. As long as that difference exists, convection continues. As long as convection continues, the magnetic field exists. Small changes in these details produce large changes at the surface. That's why the field wanders and flips. Not because the dynamo is failing, because it's chaotic, sensitive to initial conditions, unpredictable over long timescales. We can measure the current state precisely. We can model the physics. But we can't predict exactly when the next reversal will occur. We can only say it's inevitable. Someday. Maybe in our lifetime. Probably not, but possibly. Scientists found sediment evidence that reversals appear in paleomagnetic records from many sites worldwide. Lava flows from volcanic eruptions preserve snapshots of the field. Each flow cools over days to weeks. The magnetic minerals align with the ambient field. The direction and intensity get locked in. By dating the flows using radiometric techniques, scientists reconstruct field history. The most reliable dates come from potassium-argon and argon-argon methods. Recent improvements in multi-collector mass spectrometers and low background measurements have improved precision. The 40 argon, 39 argon age of the Brunhes-Matuyama boundary is now constrained to 781,000 years, plus or minus 3,000 years. That uncertainty is tiny on geological timescales. It shows how far dating techniques have advanced. The evidence is clear. Reversals are global. The entire dipole flips, but the transition looks different at different locations because of non-dipole components and local crustal magnetization. That complexity makes reconstruction challenging. Requires data from many sites, requires careful cross-checking. The work continues. Every new core drilled adds information. Every new lava flow sampled refines the picture. In July 2025, researchers used GGFMB, the global geomagnetic field model for the Matuyama-Brunhes reversal. The model covers 900,000 to 700,000 years ago, includes late Matuyama and early Brunhes, allows investigation of the Kamikatsura excursion around 888,000 years ago. That was a failed reversal. The field tried to flip but didn't complete the transition. An excursion, not a reversal. The GGFMB model suggests the Brunhes-Matuyama reversal began around 799,000 years ago. Non-dipole components increased, axial dipole decreased. Transitional fields appeared first in high southern latitudes and equatorial regions. Minimum dipole around 780,000 years ago, stabilized in normal polarity around 770,000 years ago. Duration 29,000 years, slower dipole decay than recovery. Lower dipole moment for several millennia before the reversal than after. Observed mainly over Eastern Asia and North America, not global. That distinction matters. Excursions don't always become reversals. Sometimes the field fluctuates without fully flipping. Understanding the difference between excursions and reversals helps predict future behavior, though prediction remains difficult. Toward a reversal. Or we might not. The field could stabilize, the anomaly could shrink. We're in a period of rapid change, but rapid is relative. The anomaly has been present for at least a century. It's grown significantly in the last 11 years. But 11 years is nothing on geological timescales. We need decades more data to see long-term trends. ESA's SWARM mission has provided the longest continuous space record, 11 years so far. The satellites are still operational. They'll keep measuring as long as they function. Every additional year adds value. The picture will sharpen. Models will improve. Predictions will get better, but fundamental uncertainty will remain. Chaotic systems are inherently unpredictable beyond certain timescales. We can't forecast the next reversal's exact timing any more than we can forecast weather a year in advance. Too many variables, too much sensitivity to initial conditions. Build resilient infrastructure. Harden critical systems against radiation. Develop contingency plans. Invest in research. Keep the satellites flying. Keep drilling cores. Keep improving models. Stay alert. That's the responsible approach, not panic. Not complacency, informed vigilance. Heat flows in patterns shaped by mantle structure above. Convection currents spiral in columns organized by Earth's rotation. Those currents generate magnetic fields that reinforce and modify each other. Feedback loops exist at multiple scales. The field affects the flow affects the field. Small perturbations can amplify or dampen. The system evolves continuously. Most of the time, the dipole dominates, stable, predictable, but occasionally fluctuations grow large enough. The dipole weakens. Quadrupole components strengthen. Multiple poles appear. The system transitions to a different state. Eventually, it settles back to a dipole, but sometimes pointing the opposite direction. Not a single event, not a clear trigger, a gradual accumulation of small changes until the system tips. The exact details vary each time. No two reversals are identical. Some take 20,000 years, some take a few thousand. Some abort midway and become excursions. The Lachance event, others complete fully. The Brunhes-Matuyama reversal. The differences depend on subtle variations in core convection. Variations we can measure at the surface through magnetic field observations, but we can't observe the core directly. It's 3,000 kilometers down. Unreachable. We infer its behavior from surface measurements and models. That inference is getting better. Seismic tomography reveals density variations in the mantle. Those variations affect heat flow. Satellite measurements reveal magnetic field structure with unprecedented resolution. 300 kilometers at the equator in the World Magnetic Model 2025. That resolution captures regional features. The South Atlantic anomaly's shape, the strong patches over Siberia and Canada. Computational power increases exponentially. Simulations run longer, include more physics, match observations better. Machine learning algorithms identify patterns in paleomagnetic data, predict transitional field geometries. The tools improve every year. How exactly does heat flow variation trigger reversals? What role do magnetic switchbacks at the magnetopause play? How do small-scale fluctuations in the outer core cascade to global changes? Can we identify reliable precursors? Are there tipping points where reversal becomes inevitable? Engineers building better magnetometers, mathematicians developing new analysis techniques, all contributing to a collective effort to understand our planet's magnetic shield. And in the meantime, 3,000 kilometers beneath our feet, the outer core continues churning, iron continues spiraling, heat continues flowing, magnetic field lines continue breaking and rejoining, the geodynamo continues running. And somewhere in that churning metal ocean, the seeds of the next reversal might already be forming. A small fluctuation in flow velocity, a subtle change in heat flux at the boundary with the mantle, a reverse flux patch growing larger than usual. We won't know until decades from now, when the measurements reveal trends, when models show consistent predictions, when the warning signs become unmistakable. Because understanding Earth's magnetic field reversals isn't just academic curiosity, it's practical necessity. Our technology depends on the field. Our civilization depends on that technology. When the field flips, we need to be ready, not panicked. Not blindsided. Ready. That means continued investment in research, continued operation of satellite missions, continued drilling of paleomagnetic cores, continued improvement of models, continued education of the public about what reversals mean and don't mean. They don't mean the end of the magnetic field, just a transition from one stable state to another. Life survived every previous reversal. We'll survive the next one, but the transition will be easier if we're prepared. In 2025, as I write this, the South Atlantic anomaly continues growing. The North Magnetic Pole continues its strange accelerate then decelerate dance. The swarm satellites continue their silent orbit. The geophysicists continue analyzing data. The supercomputers continue running simulations. And the outer core 3,000 kilometers down continues doing what it's been doing for billions of years, generating our shield. Our protection against the hostile radiation environment of space, a shield that wanders, that weakens and strengthens, that occasionally flips completely, but never disappears. As long as Earth's core remains hot and convecting, the magnetic field will exist, different from month to month, from year to year, from millennium to millennium, but always there, always protecting, always strange,